if you can hear me. Okay, yep, great. I'm going to provide a kind of a general overview talk about a major project that's going on right now, a joint project between the US and the UK to study Antarctica's largest unstable glacier, Thwaites Glacier, and the ocean around it. It's potentially a significant contributor to sea level rise over the coming few centuries. It could begin to change the rate of sea level rise significantly before the end of this century, and that's why it's drawn a lot of attention and earned this this joint effort by the two nations. That's a picture of Thwaites Glacier from a recent cruise by the Palmer, so you can see what the front looks like. We're going to take a look at a little bit more of Antarctica, a bit of a tour. Why is that not advancing? Okay. I've been to Antarctica a lot, as Craig mentioned. Actually, now there's been a couple more trips south because of the Thwaites project. And those dots are all the places I've been to. So yes, I've seen a lot of the continent and written quite a bit about ice shelf breakup and how icebergs inform us about ice shelf breakup. A bit about Thwaites Glacier more recently. Early on, quite a bit on the Sipal coast. And then there were several expeditions to East Antarctica, mostly looking at unusual air-snow interactions and the formation of these very large dunes. A couple of trips out to look at sea ice as well with the Australian ship. A lot of Antarctica looks like this. This is a picture from East Antarctica of the traverse. Those two dots in the distance are other vehicles almost as large as these two that you see here, crossed from the South Pole to the Norwegian base called Troll, an area that had not received a lot of geophysical mapping before. So there was quite a few geophysical surveys along the way. This was back in 2008 and 9. And a lot of the surface looks about like this in West Antarctica, where it's a little more humid. There's also more snowfall. So the accumulated snow gets reshaped and eroded into these wave-like features, dunes called sastrugi, and they cover much of the surface. And then, of course, near the coast, there are these gigantic glaciers that are draining the ice off the continent. This is actually in the Antarctic Peninsula. One of the things that impressed me about Antarctica, I don't work much in mountain glaciers, and maybe there are mountain glaciers that give the same impression, but the idea of an entire landscape that's flowing is really strong, especially in the peninsula, but in a lot of places in Antarctica, you get this visceral, obvious sense that the ice is in motion, that the entire landscape is in motion and changing, which is exciting. As a geologist, I think one of the things that's attractive about climate science and glaciology is that it changes within, well, quite a bit actually, within the period of a career. So a project can actually witness changes, make predictions, and actually see them unfold. So again, a map of Antarctica, just to introduce some of the structure of the continent, and then we're going to focus in on why Thwaites is so important. This is a map generated from illumination of a DEM built up from thousands, many thousands of stereo images that were acquired in the 2000 teens mostly. This is the REMA. That's the reference elevation map of Antarctica that was produced several years ago. This is another way of looking at Antarctica. It's a map of ice flow across the entire continent that's been generated by both radar methods and feature tracking from visible imagery. So you can now see that Thwaites actually is a wide glacier. It's grounded ice, and yet it has the appearance of some of these very wide ice shelves in terms of the structure of its flow, and it reaches into nearly the center of West Antarctica. Pine Island is another major glacier that's also contributing quite a bit to sea level rise. It looks like Thwaites is has a greater potential for instability in the near future if things unfold the way it appears they are. And here's a bedrock map. So after accumulating many thousands, over many years, many thousands of profiles using radar of the ice and the bedrock below, British Antarctic Survey assembled this map with collaboration from 50, probably 80 scientists to create this bed map of Antarctica. I believe this is bed map 2. It also includes the bathymetry around Antarctica. And it shows that Antarctica is kind of two different continental type land masses. Well, one continental land mass and a cluster of islands that are partly composed of continental type rocks, volcanic rocks like andesite, but also with some deep ocean basins and rifted crust in between. I'm not sure if you can see my cursor. We'll give it a try. This area here is known as West Antarctica. This finger-like area of high ground pointing towards South America in the upper left is the Antarctic Peninsula, basically an island if you remove all of the ice from it. Then there are several areas of high ground in West Antarctica, but it is currently completely overlain by a very thick ice sheet over the grounded area. These smoother areas are the ice shelves. So the topography there is a bit more inferred because radar doesn't penetrate through the ocean water. It's from seismic and gravity. What you can see, though, is that the center of West Antarctica is actually quite deep and is a rift basin. So this whole area has been spreading over the past few million years. It appears to have mostly ceased spreading at this point, but the ice is overlaying some very deep bedrock, which is a problem. The edge of the ice sheet to the north is fairly shallow. The ice fronts are all resting on this shallow bedrock, but if they retreat at all, they go into this much deeper area behind them. There's a very thick column of ice over the top, and this leads to an instability that's one of the main concerns about Thwaites' future and the potential instability of West Antarctica. So looking at the last IPCC report and what they had to say about sea level rise, you guys have probably seen this graphic a few times before. But what you're looking at are the various scenarios depending on how well or how poorly we control greenhouse gas emissions in the coming century. You can see the estimates for sea level rise by 2100. But the dotted line flying above all of them is one that they decided to add this time. In previous IPCCs, they simply had words saying that we're unsure, but it looks like there's a high potential for increased sea level rise. The dotted line that you see here is a line that's based on the potential that the major ice sheets have, in particular Antarctica, for vastly contributing to sea level rise should certain processes that I'll discuss, marine ice sheet instability, take hold over several areas in Antarctica. And number one among those areas in Antarctica would be the Thwaites region of the Thwaites Basin. So what you can see is that it might contribute as much as a meter of sea level rise by the end of the century if several basins got involved. Thwaites alone would not be able to contribute that much by itself, but would be a substantial fraction of that meter of sea level, additional sea level rise if it were to unfold quickly and rather sort of the worst case scenarios coming from the models. You can see there that we've already experienced quite a bit of increased rate of sea level rise, and that's really the main concern. It's not so much, well, a poor way of looking at it is 1 meter by the year 2100, because what's really important in terms of protecting infrastructure, the amount of money that economies will have to spend defending the coasts and the cities has to do with the rate of sea level rise. If the rate is much higher than it is today, then all of the infrastructure that's on the coasts and all of the insured property that's on the coast will need to be protected or moved sooner than people are expecting. For example, if you build a sea defense that's intended to last for 50 years, and yet it only lasts for 25 years because the rate of sea level rise is faster than it was designed for, then of course you have to make that very high expense, again, much sooner than expected. That, I think, is the main problem. We're going to have higher seas in the future, inevitably, but defending against higher rates of sea level rise by turning down on the amount of carbon dioxide and methane that we put in the atmosphere is the best path for having a manageable future. Here's a present day trends for sea level rise, and I might be talking to an audience that could produce 3 or 4 of these different examples of what the rates of sea level rise are in the present period of time. You can see, and as you all probably know, that the 2 main contributors to sea level rise are loss of ice from glaciers, mostly at this point, but also the ice sheets are contributing significantly now, and heat, thermal expansion of the ocean. And yet, as I tell public audiences, it's not as though it's just like adding water to the bathtub. There's a very complex distribution of sea level rise around the world having to do with shifts in the wind, changes also in how the ice sheets and major glaciers will basically change the shape of sea level because they're losing ice. And you can see also that there's been a noticeable increase in the rate of sea level rise in the combined curve, even since 1995. There are vast investments already in defending against rising sea levels at all of the, at many of the major coastal cities on Earth. And of course, storm surges are the real problem here. This is a town in England that is dealing with the problem of having a railroad that's a little too close to the seawall. This sort of loss of infrastructure because of basically storm surges on top of sea level rise is going to be an increasing problem in the future. Now, in the past, I mean, what we're talking about for the rest of this century are some fairly eye-opening rates of increase of sea level rise. Has this ever happened in the past? And the answer is yes. At the end of the last ice age, as the Earth was transitioning to a very rapid warming, rapid by geologic standards, not by present day standards, which is much faster. Still, within the space of a few centuries, we saw sea level rise by up to 4 meters per year, more typically 2 meters, per century, 4 meters per century in these rapid periods. This meltwater pulse 1A is thought to be contribution from major areas of Antarctica and possibly remnants of the Scandinavian and the Laurentide ice sheets in Northern Europe and Northern Canada as they were rapidly retreating. Still, it shows that it's possible to get sea level rise rates that are greater than 1 meter in a century, which is quite a bit more than we've seen at any point during the history of civilization, if you will. I mean, this is everything that we've done, and since the discovery of agriculture has seen very stable ocean conditions compared to the recent past. Of course, going further back in time with ice ages and interglacial periods intervening, there's been wide swings in sea level rise. What we're used to is a fairly stable coastline. And so the current increasing trend is a concern. Why did we pick on Thwaites as a place that was maybe the most important in Antarctica to study? This is a map of elevation change since 2003 to 2019. Actually, an average of several years starting with 2003. So the mean would be about 2004, 2005. And then this other satellite began in 2018 and 2019. So the difference between those two elevation maps highlighted areas that were undergoing very rapid ice loss and a few areas that are thickening. Much of the East Antarctic is slowly thickening, but the scale is quite a bit more contracted on the on the plus side than the ice loss in red and even in purple on the elevation loss side. And it shows that Thwaites Glacier really sits in the center of an area that's really seeing very rapid loss. I guess I'll jump ahead and say that the reason is that warm ocean water is eroding the front of the ice sheet here and causing it to flow out faster than can be replaced by snowfall over this large catchment at Thwaites or at Pine Island or along that coast to the south here. This is called the Getz ice shelf here. So this really is draws your attention when you put a map together like this. What areas are the ones that are really changing rapidly? There's a huge area with Thwaites at the center of it that is changing quite rapidly, that is losing mass quite rapidly. About 150 billion tons per year. I think you're going to hear that there's some interesting news this year. It looks as though the accumulation in Antarctica actually was so far above normal that it will not be a net loss this year or very close to balance. But over the past 20 years, it's averaged about 150 billion tons of net contribution to sea level rise each year. Oh, I should say, and earlier in the previous couple of decades, it was more like 50 gigatons per year. So it's increased in the last decade. Another view of Thwaites Glacier laying sort of in this keystone position within the West Antarctic Ice Sheet. And then if you were to remove the ice, you can see that Thwaites Glacier overlies some of the deepest areas in the West Antarctic ice sheet. So there's a very tall column of ice on top of this very deep ocean basin. You can see that there aren't any huge mountains that are obstructing the outflow at the front of the glacier, but it is quite a bit shallower there. And so if it begins to retreat, it will step back into deeper and deeper bedrock, and the ice above it will climb in elevation, at least initially. And so what you'll see is faster flow. Ice moves under its own weight. As you step back from a coastline like the one near Thwaites, you get a taller and taller column of ice and a steeper slope. That's the driving stress, both the compression and the surface slope, leads to faster outflow as you retreat from the edge. Right now, you can think of that shallower coastline as bracing Thwaites Glacier. And as you erode it, it wants to flow out more rapidly because it's less well braced as it retreats. So why is this area changing? I mentioned in passing before that warm ocean water is reaching up and brushing against the coastline of Antarctica. And what's causing that to occur more now than it did in the past is a change in the wind pattern around Antarctica. Antarctica is dominated by a pattern of westerly winds. They're actually called the westerlies. Or the west wind belt, and the current that it generates is called the west wind drift. What's been happening over the past several decades since the 1970s is that these westerly winds are increasing in speed. And it's thought that they're increasing in speed because of the influence of tropics getting warmer, in particular the tropical Pacific. That by the tropical Pacific getting warmer, Rossby waves essentially fronts, cold fronts, are they warm fronts? Anyway, fronts are emanating from the Pacific, and net effect of those hitting the higher latitudes is to increase on average the westerly wind speed. Well, in the Southern Hemisphere, if you push on the surface of the ocean, if you push on things, they want to move downwind, but also to the left because of the Coriolis effect. And what that does is tend to push the surface ocean water away from the coast of Antarctica. And by pushing the surface water away, you have a tendency to draw deeper water in to replace it. Push wind away from the coast, that coastline water is replaced by water flowing in at depth. It's a little bit more complicated, and a recent publication by David Holland explains it a little bit more. What you can see in the right-hand figure is that there's a combination of coastal easterlies. This is basically what happens when the downflowing winds off of the ice sort of turn to the east as they hit the coast. It's basically the katabatic wind pattern around the continent. And so with the easterlies driving the near coastal water closer to the coast and the westerlies driving winds away from, I said coast, and what I should have said was the continental slope break, which is exaggerated right here. What you do is you raise this thermocline. There's polar cold water here. It's being pushed in two directions away from the continental break-in slope because of the particular position of the continental break-in slope near this coast of West Antarctica. And so what you allow to happen is that the warm water, which has always been there, it's not a factor of global warming that's warming this ocean layer, it's that it's being moved to places that it wasn't visiting as frequently in the past. It is allowed to rise by raising the isopycnals up over the lip of the continental shelf break, and then flow down in to reach the coast of the ice sheet along some fairly deep troughs that the glaciers themselves created during periods when the ice sheet extended out further towards that coast. So here's the deep ocean out here in that indigo color. You can see the shallower continental shelf here. All of those dots are oceanographic measurements that were made quite a while ago, over 10 years ago. You can see this complex series of canyons here that were carved by Pine Island and Thwaites and other glaciers. It's these deep troughs that are allowing warm water that's been drawn up at this edge here by the contrasting winds that I mentioned to flow into these channels and reach the front of these major glaciers with water that's 3 to 4 degrees above the melting point at depth. With depth, the melting point changes. It drops because of the pressure. Therefore, if you bring in water that's a degree above zero, it's actually 2 or 3 degrees above the melting point at pressure. These ice fronts are over 1,000 meters deep, some of them. And so, so that pressure is a significant effect. So with this warm water coming in along these canyons and eroding the underside of the ice fronts, what you see is faster ice flow. And basically a pattern of rapid crevassing and upward progress of new crevasses as the ice sheet basically tries to chase downhill as the bottom is being melted out from under it. This lower part of this movie assembled from Sentinel-1 data. It shows the main faster flow area of Thwaites. However, this entire area from top to bottom is considered part of Thwaites Glacier and is moving at a fairly reasonable speed. If you look carefully, you can see there's new patches, new fields of crevasses opening as this progresses. The other thing that's important to note that's been in the news quite a bit lately, and part of the work that I did along with a team of people at Thwaites, is studying this area here, which is currently an ice shelf that's being braced by some shallow seamounts, subsea peaks in this area here near the ice edge. If you watch through this time series, you can see there are major cracks opening up across this ice shelf. And it's clearly being braced by pushing against these low hills within the ocean. This is likely to break apart completely within the next 10 years or so, possibly less than 10 years. When that happens, there'll be less backstress, less resistive force to flow for this section of the ice. And so we're anticipating that speeds like this will eventually also be the case in this area here. Now the red, the rest of the ice sheet is, of course, up to the upper right. It's flowing out towards the lower left. The red line marks the line where the ice went afloat. I believe that's the 2020 grounding line. It has been retreating, again, because of the melting at depth. So that red line, if I were to show you the time series, there'd be a series of lines stepping back into the upper right over time. And basically, that's where we stand now with the acceleration of ice. So we wanted to study the entire system because clearly this is a critical area that's changing rapidly. And this complicated graphic, I accept that, tries to show all the different components of the system that might be studied. I mentioned westerly winds. The Amundsen Sea low is sort of a component of that westerly wind pattern. There's a tropical Pacific influence that's increasing the Amundsen Sea low and the westerly winds on the outside of the loop of that. You're also seeing circulation of water underneath. I mentioned the circumpolar deep water, this warm deep water that has always been there, but is now being induced to come up onto the continental shelf and flow down to the grounding line. This is a critical area right here for change, the area where you get a lot of basal melt because of this warmer water touching the underside of the ice, and then flows out. There's a bit of a buoyant plume that's formed because as you dissolve in fresh ice, you lighten the density of the seawater. Calving studies have also come into play. We're interested in the snow accumulation and what drives that and what its likely future is as well. And I mentioned here the future cliff calving front. I'll talk a little bit about that, and you'll hear that more about that from Jeremy Basis next week. So that was a diagram of the pardon me, system. This was sort of a schematic of all the different instruments we proposed to place on it in this international Thwaites Glacier collaboration, US and UK, plus several other countries collaborating on studying this one glacier. The three main contributors, Germany, Sweden, and South Korea, have been helping us with logistics and research and researchers involved in the project. There are 8 funded projects for this. The ones shown in the dark blue color, sort of near the upper part of the graphic, are modeling studies. Dominoes is focused on calving studies, and Jeremy Basis leads that study. Profit is one that's interested in the long-range future of Thwaites Glacier and how it will improving the details of how it will come off of the West Antarctic Ice Sheet and contribute to sea level rise. And then you see several other acronyms there that have to do with different components of the system that they're going to be studying. For example, Thor is Thwaites Offshore Research. MELT simply is studying the impact of melt. I probably should have put them a little closer to the grounding line because that's where they work. Tarzan, Thwaites Amundsen Research and network meaning a network of surface stations that are studying the ice shelf in particular. Time and Ghost studying more the interaction of the ice with adjacent ice or the ice with the bedrock below the glacier. And they'll be more active in the next few years. These other studies have been active for the first half of the project, but it wasn't possible to accomplish the entire mission all at once with the available logistics. So the 2 projects here, Time and Ghost, are delayed somewhat. My contribution was a station that had a number of sensors on it. You could say it was a weather station, but it really had quite a bit more than that. A precision GPS was associated with it, a camera, a distributed thermal sensing system, basically a way of profiling temperature in detail through the ice and into the ocean below using a fiber optic cable. Other sensors, snow height to measure the accumulated snowfall, albedo, several other bits of information, and then also a complete weather station, although a compact one, but a complete weather station for tracking the weather. 2 of these were installed. When we installed them, we drilled all the way through the ice and lowered the cables down into the ocean below. I should have included the more technical schematic with ocean instruments and this fiber optic cable extending to near the seabed. So we have a lot of information about the ocean below and the conditions above on the ice. The interior of the ice doesn't change much, but we do have a very good temperature profile through that ice, which has to do with its stiffness and strength for modeling. And those 2 stations plus ocean cruises around the outside of the Thwaites floating ice have already led to some improvements in understanding the details of ocean circulation under the glacier. That a lot of the warm water is actually coming from after having made a trip in front of Pine Island, which is to the right in this map. Cavity and channel, those two labeled red dots there, are the sites of the two AMIGOS stations. I should explain that the AMIGOS is an acronym. It stands for Automated Meteorology Ice Geophysics Observing System. So the two stations there are giving information about the ocean. The data is uplinked through an iridium on a daily basis. And so we were able to begin studying ocean conditions and currents, and also the weather and the GPS motion field, while the stations were out there for the past 3 years, 2.5 years. And so you can see we've unraveled a bit of the circulation underneath there. These are actually vectors for the currents at the deepest sensors underneath the cavity and channel site, and beginning to get more of a detailed map of what's going on, rather than that simple schematic that I showed before with straight lines and circular motions. So one of the major concerns about what might accelerate the retreat pattern at Thwaites is ice cliff failure. And I don't want to go into too much detail. Jeremy Basis is going to discuss results from his whole team, which is listed there at the top: Brandon Berg, Anna Crawford, and Doug Ben, looking at different ways that ice will fail under various conditions. And there's 3 examples shown in the left-hand side here. A land terminating glacier that's got a 135-meter high cliff, and you see that it rapidly slumps, collapses, builds up a hill of crumbled ice in front of it, and stops being quite so active because basically the singularity imposed by this knife edge 90-degree angle here is gone because it's collapsed a bit. When you start to put the glacier in water, up to sort of its neck in water, almost floating, then you get different characteristics. You can see the same kind of slumping occurs with rotating blocks. And of course, because these things are smaller in their minimum dimension than they were when they were standing up as a cliff, these things can float away and expose a fresh edge. And when you get a very thick column of ice that's nearly afloat, then the aspect of surface slumping leading to an unsupported block lifting up off of the seabed and breaking off and floating away comes into play. This is the pattern that leads to very rapid, potentially very rapid retreat when the geometry is appropriate for that kind of rapid calving, and when surface currents, or possibly melting, can remove that crumbled ice away fast enough to keep it from building up and providing a backstress that suppresses the rapid calving that occurs when you've got a tall column of ice almost floating in water. This happens in nature. It's been seen at a couple of glaciers in Greenland, and most especially at a glacier called Helheim along the eastern Greenland coast. There are cameras and other instruments that have been placed by helicopter on this glacier, cameras that are watching the ice front from the shore, and then GPS that are on the ice itself that show these blocks rotating and calving and eventually floating away, although this crumbled area does provide quite a bit of back stress that props up this ice front so that the calving rate is a little bit slower than it would be if this were cleared away rapidly. It also occurs in Antarctica, at least we think so. It appears that this glacier called Crane Glacier in the peninsula, which has a very deep fjord underneath it, and recently had a very rapid ice shelf removal. An ice shelf collapse occurred in 2002 that left a very tall cliff at the front of Crane Glacier, which is still grounded because it's so deep. The fjord is quite deep and the ice is very thick. So cliff-like calving events have been observed across the front of this glacier as well, giving us another example to look at and compare to the geometry in the future that we expect at Thwaites Glacier. This has a significant impact on the rate of retreat. This study is a little bit old, and I think Rob DeConto would probably modify this now if he had another go at it, but it was included in our summary paper that was sort of the marching orders for undertaking the Thwaites project. And what you can see is that basically where he says ocean warming only, that's the present day situation where you've got erosion at the base of the ice because of warm ocean water. And by increasing the temperature, frankly, to somewhat unrealistic levels. Here you can see you get a significant retreat of ice, but if you include atmospheric warming, and what he means by that is if you include ice cliff fracture, ice cliff calving, because he uses atmospheric warming to flood the surface and induce rapid fracturing. What you can see is that you greatly accelerate the pace of ice sheet loss and sea level rise by adding in this extra component of ice cliff calving to the model. So in summary, that's what we're up to in Thwaites Glacier. It's a major project that I think you'll hear more about in the future. There's several results from the first cluster of projects that have been working together that'll be coming out, have been coming out, and will be some more by the end of this year and next year. And then the other studies will start to look further upstream at some of the areas that will come into play, become more important as the retreat continues in the decades to centuries to come. And so I'd be glad to take any questions now. That's some of the slides that you just saw to help you sort of remind you where your questions might be. Thanks very much.
Thanks so much, Ted. That was a fascinating talk. Do we have any questions from the group? Feel free to raise a hand or mention so in the chat.
I can't see the chat, so I'll count on you, Craig, to let me know what's going on. I want to keep this up on the screen. I guess I could escape and it would still be partial screen mode. Yeah, I'm still sharing the PowerPoint mode.
There's a message from Christopher Schumann in the chat, which is I think, I'm not sure if it's a question or an extension. It's an image, I believe.
It needs help.
Just a visual. How big the changes have been. Ted, it's been a bad year for sea ice around Antarctica, as you guys have posted from NSIDC. Can you speak a little bit more to the role of sea ice in helping to stabilize some of these ice fronts? Either ice sheet?
Yeah, that's true. Sea ice hit a record low this year at the seasonal minimum, which in Antarctica is in February or early March sometimes. In late February, it hit the record minimum in the 44 years that we have continuous data for sea ice extent. And yes, sea ice does protect some of the ice shelves. It's not a huge factor along the coastline of Pine Island and Thwaites because it's rare that those areas are completely ice-free. One of the ways that sea ice protects ice shelves is by suppressing flexure due to wave action from the Southern Ocean, from the ocean, the global ocean at large. And so this year, many areas of Antarctica were exposed to wave action and fairly warm conditions because of the absence of sea ice. And a few places like the area in front of the Larsen, which no longer has an ice shelf, but has had persistent fast ice for the last decade, have seen breakouts of that fast ice because of the low sea ice conditions. Ironically, even though it was a record low, the cruise that we had this year that was aimed at Thwaites primarily could not get close to Thwaites because the one stubborn patch of ice that remained this year was right in front of Thwaites and Pine Island. So they worked a little bit further offshore and at an adjacent area that shows some of the same processes. Gavin, if sea ice is being affected by the anomalous fresh water, then a good year for the ice shelf might imply a bad year for sea ice. There's a lot of talk about what the impact of this fresh water and the additional contribution from the continental ice sheet might be. But one of the things that stuck in my mind when I started to look at this, the total volume of sea ice is, I'm going to forget the exact number, but thousands of cubic kilometers. And the net imbalance of the ice sheet right now is on the order of 100 to 200 cubic kilometers, or billion tons of ice. So the freshwater impact is, well, on a continental scale, not very large. In localized areas, it can be a significant factor, somewhat fresher water in areas of rapid melting. But by and large, it's a tiny impact on the salinity and therefore the freezing point, for example.
Next up, we have Olga, I think.
Yes, thank you. That's great to see an update what's happening over there. Mostly mine is rather a comment than a question, and it's about instabilities. Glaciologists so kind of hang up or like the word instability, and both of them are hardly, by both I mean marine ice sheet instability and marine ice cliff instability. Both of them are hardly applicable to Thwaites as it is. So I'll post in chat links to two papers, one by me and Duncan Meehan. One is about specifically focusing on Thwaites topography. And effectively, it's not as simple as a retrograde slope. So there are many other things. And the other one, it's about marine ice cliff instability, and it determines the stability condition for an ice cliff. Again, it depends on like dozens of parameters in bizarre combinations and everything. So this is just not to say that Thwaites does not lose mass. It does. It just the interpretation why it does it. It's most likely lies somewhere else. This is not a simple just say, oh, because the bed is retrograde, there's marine ice sheet instability. They are done solving the problem. Similarly with the cliff. So kind of these are most likely not explanations. That's my comment.
I think, in fact, the way to put it is that the sophistication of the marine ice sheet instability or the marine ice cliff instability will progress as science generally does. I think you'll hear from Jeremy next week that while he's resolved some of the different models or modes of ice cliff fracture effects, it does take a specific geometry and flow rate in order to really get to the point where those cliff calving styles actually occur. And it's not as though it's likely that Thwaites will undergo this rapid ice cliff calving across the entire front for an extended period of time. There'll be isolated periods when ice cliff failure of some mode will take hold as Thwaites is retreating. And I'd like to resolve that as part of the Thwaites project. In terms of the marine ice sheet instability, yes, there are complexities, of course, like there is with everything. And it's as we get more detailed bed slopes, ice bed shear models and fracturing and retreat, that model will improve also. But the fact that the Thwaites and Pine Island area were likely the gateway for rapid ice loss during the past ice ages is sort of in the record, both in publication and in the sediment cores off the coast of the Amundsen. So yeah, there's going to be some more sophistication to those two models. But in terms of the two directions that people started down in order to understand why Thwaites is retreating and why it might be a significant threat to sea level rise in the future, those are the two paths, the two ideas that people began to work with.
Just one comment on that, and again, by no means I'm arguing, rather there could be something else, and just focusing on these two might kind of, leave resources focused on these rather than looking in more broad and trying to find other potential explanations. That's
fair enough. Yeah, fair enough. And of course, 6 of the 8 studies are really observational in nature and not so focused on modeling. And I would say that the Dominoes project and Jeremy's ice cliff work, along with Doug Ben and Anna Crawford, you're going to be pleased, I think, with the fact that they are distancing themselves somewhat from the idea that the entire front of Thwaites might suddenly undergo rapid, unstoppable calving and lead to the very rapid retreat that Rob DeCanto and David Pollard were talking about in the first incarnation of ice cliff failure, which they were using to try to explain basically marine meltwater pulse 1A in the past. But okay. More questions?
So
Yeah.
next other question, Rota, is thank you ever so much, Olga. So we have Jeff has his hand up next, I believe.
Hi, thanks for the tip for that. I've had a quick look at the long record of buoys at the shelf break, at tethered moorings, the shelf break, and it's clear that there's quite a lot of variability in terms of the warm water coming up at the shelf break. Has the record been extended much? Do you know how many years of observations there is now?
No, I don't. I know that the latest crews made a number of CTD casts all along the front, well, within the Amundsen Sea embayment. And also there's data from instruments mounted on seals, basically elephant and Waddell seals. So they get quite an image actually over the course of the year that the instruments stay on of what the ocean conditions are like. The Amigo stations and the other data showed that water of more than 1 degree centigrade above zero is present in the lower 150 to 200 meters of the ice shelf cavity right now, moving rather slowly. And also that a good portion of the water column is, as I said in the talk, imported from Pine Island and has already got a small meltwater component added to it. This will be a paper coming out by Tiago Dato, working with Karen Haywood in the near future. So I'm not familiar with the ups and downs of that isopycnal at the continental shelf break, but yes, we have extended the record of observations quite a bit with 3 cruises as part of the ITGC.
Thanks.
Thank you, Jeff. I think next is Stephen. Has his hand up?
Yes, hi. Thank you, Ted. I really enjoyed this talk. I learned a lot. And so in some of your slides, you started mentioning about on how the westerlies are controlled by the tropical Pacific. And I'm actually more of a deep time person. I work in the Miocene and the Oligocene. Mm-hmm. And so the Holocene and recent is kind of new to me, and the complexity between the interaction between the tropics and high latitudes is intriguing for me. So could you maybe elaborate a little bit more about on how the tropical Pacific, or ENSO basically, is affecting West Antarctica, as well as the southern annual mode and how they interact with each other and how this all plays in together?
Yeah, so when I said that the westerly wind belt increases in speed, that's basically a way of saying that the southern annular mode is trending towards a more persistently positive state. I'm going to get a little out of my depth if I'm low. Okay, trying, let's see, get a little bit out of my depth trying to explain Pacific warming and its influence. You use the word control, and I think the word influence ought to be the word that's used, because the westerlies are a basic feature of Hadley cells, fundamentals of Earth circulation, heating at the equator and cooling at the poles. But the tropical Pacific apparently teleconnects with the westerly belt through Rossby waves, basically due to increased vertical convection over the Pacific as it warms the central Pacific. I'm told that, let's see, it's the PDO and not ENSO, although they are very similar patterns, but one of them is a more sort of persistent decadal pattern. PDO, Pacific Decadal Oscillation, in the warm state has a strong influence on the westerly wind strength around Antarctica. And then this component that David Holland pointed out, the easterlies and sort of wind shear, although he doesn't use that word, but the winds blowing in opposite directions happen to lie. Paul Holland and David Holland have both pointed this out. That shear zone happens to lie over the continental shelf break, which on average tends to push the surface water away and raise the isopycnals across the continental shelf break. And that has led to warm water filling these deep troughs in the Empson Sea embayment. Did I get your question well enough? I'm afraid I'd have to refer you to papers by Eric Steig, Paul Holland.
No, that was a great intro. It's up to me now to go to some of these papers. Thank you so much.
Eric Steig, also not so much Kyle Clem, Ryan Fote, and Paul Holland have all written recent papers that attempt to, that do show a link between warming in the Pacific, Rossby waves, and the westerly wind belt.
Excellent. Okay, thank you so much.
Sure.
Thanks, Stephen. Now we've got a couple of questions in the chat that I'd like to go to. I know Vivian is waiting. However, I think Gavin just made a question that was relevant to the last conversation.
Vivian, like she's been waiting. So don't.
Sure. So Vivian, would you like to unmute?
Yes. Can you hear me?
Yeah.
Yeah. Anyway, I was intrigued by one of the slides that you showed. Where there over a period of time there was this increase in fracturing and rifting on the ice shelf there in front of Thwaites. So I'm just wondering how many years would you estimate that it would take for that portion of the ice shelf to completely break up? And would that be enough to trigger off the marine instability?
Yeah, well, you can argue with Olga about what happens after the ice shelf breaks away, but we're thinking that the ice shelf will probably break away within 3 to 10 years. That's two different papers. Karen Alley wrote one that was published middle of last year, and Christian Wild had a somewhat more detailed study that was just published a couple of months ago in the cryosphere that tries to estimate when the Thwaites Eastern ice shelf will break away. Will no longer be connected to those rumples that are off the coast there. There's actually several new fractures that have appeared. I think they were just starting right at the end of that particular movie that are going to break that ice shelf up into several large icebergs within a few years. And in fact, it may not be that easy to revisit the site, which is being planned currently for this next coming summer field season, southern summer field season, because the cracks are going to be going right through the area where the Amigos were installed, which is sort of the center of all of the geophysics work that was done as well. So they may have to land somewhere else. Did that get your question, Vivian? And I could show that movie again.
In part, but would something like that be enough to initiate a real marine instability?
So that ice shelf has already begun to flow faster. It's increased in flow speed by about 25 to 30% just in the last couple of years because it's coming apart. The acceleration of the grounded ice doesn't extend very far upstream yet. The grounded ice upstream of where that ice shelf is, it certainly doesn't have 25 or 30% acceleration and flow speed, but it does show some acceleration above the grounding line as this ice shelf begins to speed up and basically cease to provide any backstress. Will it start the marine ice shelf instability? No, I think what will happen is that slowly the fast flowing part of Thwaites will widen across that same area. There is somewhat higher ground upstream of the ice shelf than there is under the fastest flowing part of Thwaites. And so it'll be a slow progression to widening and acceleration after the ice shelf is gone. But that'll be another step in the increased mass loss from Thwaites Glacier.
Thank you.
I think next up we have Gavin.
Yeah, I'm intrigued by why you think that the westerlies are only being affected by the tropical Pacific, when we know that they've been affected by the ozone hole. We know that they're being affected by direct impacts of carbon dioxide, right? We have tons of attribution studies in models that demonstrate that the long-term trends in the southern annular mode are very well explained by just the radiative effects of the polar ozone hole and CO2. And so you're looking at something like the PDO. There hasn't been a huge trend in the PDO. There hasn't, there's a lot of interannual variability in the ENSO teleconnections. Why is that the driver of the trends?
I didn't mean to imply that it was the driver of the trend. I agree with you that the ozone hole has been a factor. It's fairly seasonal. The ozone hole and its effect, I think, was modeled as being seasonal on the westerly winds. Warming conditions generally around the tropics could be linked to CO2. I think you might also be referring to, it's a little bit old paper now, Arblaster and Meal linked the stronger westerlies to increased CO2 also. But several papers have made the connection between the Central Pacific warming and increasing westerlies and increasing strength of the Amazon Sea low. And I leave it at that. That's part of the story. But the ozone hole was also invoked, especially in the like around 2010, the years after. I forgot her name. Susan Solomon, and Dave Thompson's paper.
Mm-hmm. Well, I mean, the reason why I bang on about this, and I do a little bit, and I apologize to everybody about that, is that it makes a difference to what we're going to predict for the future. If the ozone hole, which was effectively a one-off thing, which will actually slowly go back over the next 50 years,
yeah,
is a big driver of the under ice shelf melting, then it will decrease in the future, right? Because we're no longer going to have that acceleration. Mm-hmm. But if the effects are a more direct impact of warming in the Pacific or from CO2, then we would expect it to continue. And so, that makes a big difference to what you would then predict for what's going to happen to the Thwaites, no?
I take your point completely, and I don't think that warming in the Central Pacific will slow down either. I think that's also connected to increased CO2. But yes, I agree that the ozone hole appears very slowly and with a lot of noise to be declining, and we'll probably spend most of the rest of the century declining. But I don't think we'll see much respite from warm ocean water reaching Thwaites, which is really the main point of what's causing the retreat at Thwaites Glacier. And
no, but you're begging the question. I mean, the issue is why the warm water is reaching the ice shelf.
Yeah.
If we're looking at a situation where the ozone hole played a big role, then it's no longer going to continue to do that. Right. I mean, it's basically stabilized at this point.
Mm-hmm. But the trend in SAM isn't particularly seasonal, if I remember correctly. The trend in the southern annular mode spans the seasons. It's, I believe. So what we're seeing is an increasing westerly wind belt, which I'm inferring is part of the cause from publications, part of the cause of driving warmer water up onto the continental shelf. I don't know if that sounds wrong to you. Let me know.
No. That bit sounds right. But okay. Well, now we'll.
I'd be glad to talk about it in email. Yeah. No. Let's. Yeah. This is good because, as you can see, it's one guy with experience in ice sheets mostly and remote sensing, attempting to comprehend enough to talk about the entire Earth system as it relates to Thwaites Glacier in Antarctica and sea level rise. And it's a pretty wide range to try to straddle.
Indeed. Yes. Thank you.
Sure.
Thanks, Gavin and Ted. I think there's a comment from Christopher Schumann in the chat. I'm not sure whether it's a comment or a question, but if you have a question, it'd be great to hear from you.
I just when Ted talks about the fast ice flow zone, I just wanted to give people a sense of scale that they might relate to a little bit better. That's all.
Mhm.
Yeah.
Okay.
Thanks, Chris. Do we have any final questions, perhaps? Silence.
Great. Okay. Well, I hope that was definitely better questions than I get from the public audiences. So thanks a lot for a stimulating exchange and some directions to look at for refining. I think in general, you're going to hear a lot more about marine ice cliff refinements and marine ice sheet instability refinements over time. I'm not sure what else we would look at except things, they may get unrecognizable, but the basic patterns of those two processes will probably continue to be invoked. And as far as exactly what's going on with CO2, tropical Pacific, and increasing westerlies, I think Gavin and I agreed that the westerlies are a big part of the change around Antarctica, and that's a big part of driving warm water up near the coast. So hopefully that came across in the discussion and in the talk.
Absolutely. Thank you so much again for talking. Hopefully we can convince you to come back sometime. That'd be lovely. I see classes clapping. A few people are saying thank you and great talk.
Great. Okay. Thanks a lot.
Thanks, Ted. I hope everyone has a great rest of the day. Thank you all for joining us.